Okay, so secure database games. Now this title doesn't make sense yet, but we'll get to that. So my name is Dominic Tarr, and so this is the name my parents gave me, and I was pretty happy being Dominic Tarr, but then I became a JavaScript developer, and I had a problem. Too many Dominics. So if there was only 2 Dominics, then we could settle this by having some kind of fight to the death or something like this. But unfortunately, Dominic is becoming more and more popular as a name. So I was born about this point, and now it's like, who knows how bad this problem is going to get. So I'm going to solve this problem once and for all. I'm changing my name. My new name is Zukad Dusan Zamaz Hobez Pudot Rotiv Gabom Holan Nenok Kodo Hataf Lizard Diffas Fila Tiju Sitaj.
We're all Scientologists now.
Yeah, so this is a much better name. So this is my the hash of my public key encoded with proquint encoding, which is a pronounceable binary encoding. So this is a much better way of naming people, because you can always generate a unique key. There's no chance that anyone will have the same name, pretty much. You can prove that that really is your name because because it's a public key. So someone could be like, "Hey, I'm Zukov," and you'd be like, "Okay, prove it," and then they wouldn't be able to sign that, so that would prove it. And also, you don't require a name registry, so we don't need to run any servers and stuff. So there's two crypto primitives this depends on, and first, I want to make sure that everyone understands these. So one-way hash functions. So if you use git ever, you've probably seen commit messages. Those are SHA-1 hashes. You get other kinds of hashes. So basically, and you may have also heard of hash tables. Now, these two concepts are very distinct. So in a hash table, you have basically an array, and you hash the items, and then you use that to choose where you put it in the array. And a big part of the design problem with a hash table is deciding what to do when you have a collision. And you want to design have a hash function that collides less, but it's going to collide eventually. And so people are used to the idea of hashes colliding. Now, for cryptographic hash, what we do is we just expand the hash to as long as necessary, so that we'll most probably never ever see a collision. So we just have to make this some big numbers to compare with things. So Twitter usernames. So there's 3 with 23 zeros possible Twitter usernames. So that's quite a big number. You've got 37 characters to the power of 15. But that's smaller than the number of bacteria on Earth. So they can't use Twitter. But that's smaller than the number of IPv6 addresses. So they could all use the internet once we get IPv6 working. Incidentally, there's enough. It's 5e to the 30 bacteria, but 38. So that means there's about 10 million IPv6 addresses per bacteria. So that should be good. Now, possible SHA-256 failures, we've got well over double the amount of zeros. So that means that for each bacteria, you could have an entire internet of IPv6 addresses worth of SHA-256 hashes. So you could hash all the bacteria, and you'll probably never run into an accidental collision. So instantly, that is slightly smaller than the number of particles currently estimated in the observable universe. So I'm not sure if this will be a problem at some point. But basically what we have to do, we just have to pick design a hash function to be long enough so that we never see a collision before the point where the universe is destroyed. So this is what sane scientists currently think might happen. So if all of these are going to be unpleasant. one, the universe crashes back in on itself, one, it expands forever, but pretty much everyone at least agrees that the universe will end at some point, including like religious crazies. They generally think that the universe is going to end much, much sooner, so rationally they require much weaker crypto. So the second thing is, so asymmetric cryptography is the other part. So this guy, does anyone not know who Rumpelstiltskin is? Okay, 2 people want me to tell the story. Okay, so this is a fairy tale about Bitcoin. So, basically, there's a drunken miller brags that his daughter can spin straw into gold, mine Bitcoin. And then, so the king is like, okay then, show me this amazing cryptocurrency. And he's like, fuck, now I'm in trouble. I need to I've hyped my crypto vaporware. I need someone to do it. And this hacker turns up, this imp, who is like, hey, I can do it. Basically, he extracts, he blackmails the daughter, the farmer that, like, I will spin straw into gold for you in exchange for your firstborn child. And they are like forced to agree to this horrible deal. But he spins straw into gold, and the king is so impressed that he marries the daughter. And then, later, they forget about the imp, and later they have a child, and the imp turns up, and he's like, you have to give me the first child. He's like, no, is there any way we can possibly get out of this? Anything at all? And he's like, no, of course not. Not unless you can guess my real name, aka private key. So the queen spends like 3 days trying to brute force the private key, just trying to come up with whatever name it might be. And she just can't figure out what it might be. However, the imp has not been using correct, basically he's careless with this private key. And he's like off in his hut in the forest, and he's dancing around his campfire and singing like, oh, they'll never guess, they'll never figure out that my private key is Rumpelstiltskin. And a messenger happens to be passing and hears this story, and later on sees the queen. Is like, you never guess what happened. I saw this crazy guy in the forest who said they would never guess that my name was Rumpelstiltskin. Who could, what a crazy thing. And she's like, oh, that's it. And so they stole all his Bitcoins. Now this story exists across many different cultures. According to Wikipedia, it's like most European cultures have this character with a different name. There's an Israeli version, there's a Japanese version, and it's generally about there's a magical creature who its powers derive from its true name, and if you know its true name, you can control it. So children already, everyone already understands how this works. I don't know why there's this myth for this throughout the world, but that's how asymmetric crypto works. So the thing I showed you before was my public name. Then I have a secret true name that I can't tell you because then you will be able to control me magically. Okay, so now that we understand crypto, programming is pretty hard. So programming is hard because you have to be completely precise. You have to think very clearly and be completely precise about what you're saying, because you're instructing this very dumb but completely obedient robot how to do everything that you want to do. Now, distributed programming is harder than that, because not only do you have to tell this completely dumb but obedient robot what to do, also sometimes it won't hear you, and there's other robots, and the messages that they send to each other could arrive in different orders, and you have to contend with the fact that light travels at a constant speed, and physics and stuff like this. Now, decentralized programming is even harder than that because sometimes the computers might lie to you. Basically, the difference between distributed and decentralized programming is distributed is about computers that you own, and decentralized is about computers that is with computers that you don't own. Now, what does own mean, really? Now, this is a word that's been in like human culture for like thousands of years, but what does it really mean? So, interesting to observe, I think, that animals don't really have property. Like some animals have territory, but they pretty much enforce their property rights over that territory personally. So like they will just beat up other animals that come into their territory. On the other hand, humans have this abstract notion of property where there's this whole system. So like the simplest is like I chain up my bike to prevent someone stealing it. But you own a house or a car because there's this whole system of laws and other people whose job it is to enforce these rights and preserve this ownership concept. So to have ownership, you need police and courts and laws and lawyers, and then you need a military to defend your property system from other property systems. And this is all to making distributed programming easier. Otherwise, it would become decentralized programming, where basically you have to assume that the other computers have free will. So basically, you have to make a game that they want to play willingly. So this is, basically there's two things you can do. You can have strict rules of the game that that you can check if they're playing the game correctly and just ignore anything that they don't do. And you can reward / punish like good or bad behavior. So that normally comes in the form of if they ask for something in an unhelpful way, then you refuse to give it to them. So in BitTorrent, there's a thing where two nodes are trying to replicate the file to each other, and they give data to the people that are giving them the most data as well. So this reciprocity is built into the protocol. Even TCP has a thing like this, where you have, like, back pressure is basically an element of this, where you slow down the message if data is coming too fast, you slow it down. So this comes to my new project, Secure Scuttlebutt. So at the data, it's a secure replicated database, and then the game is something you build on top of it. So the data model, there's three important things. There's identities, which are public private key pairs, messages, and then messages are combined into feeds. Here is a little picture of one feed. So each of these is a message, and the first message contains the identity, and the next message points to the previous message by having the hash of the previous message in it. That's represented as this arrow. Then under each message, there's a signature that signs that message and proves that it's from the public key. So you can receive this from anyone and verify that this is valid. Then the feeds can refer to each other. So this could be one feed, and then it makes a follow message that points to another identity. And now these two feeds are cryptographically linked together. So this feed points to this whole other feed. Another situation is you could have someone posts a message, and someone posts a reply to that message, and then you have another reply to that reply. And now these individual messages are cryptographically linked. And this has some interesting properties because at this point, so a hash, to know the hash of something, that thing has to already exist. So these arrows always point backwards in time. So we know, we can verify cryptographically that this part of this chain occurred before this part of this chain. And that this part of this chain occurred after this part of this chain. And so this one, this message could have been before or after this message, we don't really know. But it was at least, but from that we can estimate like the relative times and order of things, and we can have a whole bunch of chains. So we get this data structure that is, we can verify even offline. So you start at your key, and then you make a feed, and then by interacting with other users, you create links to other feeds, and then you get a growing data structure where you have one bit that's centered on you, so you're your own central authority, and then your data structure overlaps with other people's data structure. So here's another example too. You could also have a message that points to some other external object. Now this could be an info hash on a web torrent thing, and then you could, make like an Instagram quite straightforwardly. So this gives us a pseudonymous trust network. But how do you calculate trust? It's pretty. I don't know exactly how to do that yet. So I'm just going to pump that to the humans. The main objective is to stop future Dominic from turning evil. So the plan is to build a system where users and myself can be confident that I don't become Mark Zuckerberg. And so this is important because how I'm going to avoid this is that I'm not going to pay for any of the servers, because if I pay for the servers, then now I have control of the whole system. But if I encourage other people to pay for the servers, then I have less control over the thing. So I can't really interfere with them or data mine everyone, and also I don't have to pay for the servers, which means I never have to get up at 3 AM to fix something. Also, conversely, this is probably the worst startup idea ever. No VC in their right mind would fund this idea, which is also how future Dominic is not going to become Mark Zuckerberg. Yeah. So this just gives us a simple data structure, and then we can make apps that plug in that create specific message types that can be cryptographically linked with other message types that are in a feed. And then these could be pretty much any kind of thing. So I want to be able to have other parties build, anyone else be able to build stuff and just plug it in. So some ideas. So something like Twitter, like solicited spam. So Twitter is like the opposite of email, because email is unsolicited spam. Anyone can just send you a message, and then you have to filter out the stuff that you want. But Twitter is the reverse. Here you filter out who you want to be able to send you spam, but once you have followed them, they will send you everything. And this works much better. Unfortunately, it's much more entertaining than email. So that's good or bad in certain situations. All kinds of other things you could do on top of this. Because I don't control the platform, I can't stop other people from writing their own clients and creating new message types. So other people could easily build apps and stuff like this. So we could, whereas Twitter or Facebook wants to prevent other people from doing that, because if someone else creates more value than them, then they've lost control of the platform. One thing that would be very useful would be a secure decentralized package manager. NPM is really good. NPM is good, but it could be gooder. Also, there is all kinds of things in this area. How am I doing for time? Cool. Okay, so one thing I've been wondering about for a while is how would you build a cryptographically secure poker game? Does anyone have any ideas? The weird thing, poker is a game about having a secret and then revealing a secret. So I thought it would be pretty interesting, but the challenge I had that I couldn't quite figure out was if I have the ace of spades, then that means that none of you can have the ace of spades. So how do I tell you that you can't have the ace of spades without revealing that I have the ace of spades? And I tried to think through this, and I couldn't figure it out. And then one day I read this other thing, and I figured it out. And then I stumbled upon a paper that the original RSA authors had written very shortly after they invented RSA about how you could have a secure poker game. I'll explain it, but first explain rock, paper, scissors, and blackjack, because they're much simpler. So with rock, paper, so to do secure rock, paper, scissors, what we do is we just pick a move, and then we reveal the thing, but we have to reveal it at exactly the same time. Because if you see my move first, then you can change your move to what defeats that move. Now, because of the speed of light, this is impossible. So what we do is we have a two-phase protocol. So I decide what move I'm going to do, and then I pick a random salt, and I hash the move and the salt together. Then I announce the hash. Now, once the other player has seen the hash, it acknowledged it, then now I can't take my move back. So now I just reveal what the hash was, and they reveal what their hash was, and then we know who won. So blackjack can be done in a similar way. So, and in particular here, I'm talking about infinite blackjack. So some casinos play a blackjack variant where, to prevent card counting, they have like 10 packs together, or an infinite, or a loop of packs that just keep on playing. So the cards are uniformly distributed, but you can't count the cards, and you can't, and just because you have the ace of spades doesn't mean someone else doesn't have it. So this doesn't interfere with the dynamics of blackjack that badly. It's still pretty much the same game, but that would pretty much ruin poker. So blackjack. So what you do is you can pick a fair random number between n players. You each just pick a random number, your own private random number, then you hash it, then you announce the hashes. Then once you've got all of the hashes back together, then so for my card, everybody sends their secret random numbers to me, and then I XOR them all together, and now I know what my random number is. And then if I choose to play that hand, I announce what my random number is, revealing what the whole random number is, but for a while, I held the secret. So I could decide what to do. If I fold the hand, no one will ever find out what card I had. And so you could play blackjack that way. Now, poker, on the other hand, there's an interesting property of asymmetric cryptography systems is that they're usually commutative. So you can encrypt something with your public key. It's rather like putting the object inside a box and then locking it. But you can put multiple locks on the box. And it's different to putting that box inside another box. So I get 52 cards, I put them all inside locked boxes, and then with the same key, which it locked with the same padlock. Then I randomize the order, then I give them all to you. Then you put another padlock on all but 5 of the boxes. Then you give the first 5 back to me, the 5 singly locked boxes back to me, and then I can now unlock those boxes because they're only locked with my key. All the rest of the boxes have 2 keys on them, so neither of us can unlock them. So you give all of the other boxes back to me as well, and now after randomizing the order, then I pick 5 of the boxes and unlock just one key, unlock only my key from that box. Now all those boxes are only locked with your key. Then I can give back those 5 boxes to you, and then you can unlock those boxes to find out what cards you have. Now we can play poker. Also, incidentally, if you have a gambling site, you know that, they can, basically, when you play poker around a table with your buddies, you take turns dealing, and the dealer deals the cards face down. So you can see they don't know what the cards are. But when you play on a poker site, it's more like the dealer sits behind a screen but deals the cards face up, shuffles the cards face up. So they know what cards everybody has. So you're trusting them not to give any signals away. Now, there have been poker sites that have cheated like this, And it would be very tempting for them to do so because, then they could have a lower rate and you'd be like, oh, what a good deal. It's more profitable to play on this poker site. But then they just have a secret player who occasionally makes a very good decision. And there's no way of being sure that any particular poker site isn't doing this. So then there's a whole bunch of other stuff that we need to make this thing working. So the idea to bootstrap this is, so we need, because of NATs and stuff, and it's difficult to do direct peer-to-peer connections. So my idea is to encourage people to run relays. So a relay will just be a server that you can run on DigitalOcean or AWS or whatever, that just needs to have a static IP address, and that will just replicate your data and the data of the people that you have linked to. And you could do like 1 to like n hops. There would just be a configuration setting. And then you'll just advertise in your feed where the servers that could replicate you are, so someone who's following you would be able to retrieve that. And this could be used also to bootstrap. So this is still decentralized because there's no, because the relay is completely generic and anyone can run it. Also, the SLA required for the server would be very low. Like 1.9 would be fine, because there'll be, as long as some people who are connected to you have servers, then they'll be up some of the time. So if you get 1.9, it'll probably work. It'll probably still work. So you could then use this as like WebRTC introduces. So WebRTC introduces is like the part of WebRTC that isn't peer-to-peer, and you need a server to connect to and exchange a thing. With this, you could have like, just people could randomly run generic servers that where you don't need, they don't need a domain or something like this. They can just be anywhere, and you would still be able to make direct peer-to-peer connections and smuggle illicit cat pictures to your friends. And then when you connect to another peer to replicate, if that's encrypted, then passive eavesdropping will be impossible. So for someone to get the data out, they'll have to actively connect to the network and partake in it, instead of just sending a letter to Mark Zuckerberg and telling them that they have to give you your data and are not allowed to tell anyone. So here's some cool links. So this is Secure Scuttlebutt is the name of the core of the module, and Paul Frazee, P-Phrase, and I are working on a thing on top of it, which is currently called Phonics, but we're going to change the name to some weird acronym. We just haven't chosen what it will be yet. And you shall hear more about this shortly. Cool, that is my last slide.